Build quadratic models from verbal descriptions and from data. So this is chapter 3, section 4. Basically, we're back to applications. When you start building models of things, that's what you're doing. You're putting applications into practice. So let's look at our first example. And a classic example of quadratic functions is projectile motion. Anytime you deal with quadratic functions, someone's going to pull out a projectile motion problem. Luckily for us in this case, it's going to give us the function we don't have to find on our own. An object is propelled straight upward from a height of 6 feet with an initial velocity of 32 feet per second. The height at any time t is given by s of t is equal to negative 16 t squared plus 32t plus 6, where s of t is measured in feet and t in seconds. Find the maximum height attained by the object. So as I said, we're given the equation. So they're giving us some background when they tell us the height of 6, but you can see that height of 6 comes into the plus 6. We've been shifted up by 6 because it started at 6 feet. Initial velocity of 32 feet per second, and you can see that 32 in the t there. So we can see where some of these pieces are coming together, but we want to find the maximum height. So let's start looking at this and play with the things that we already know about quadratic functions. So our formula, s of t is equal to negative 16 t squared plus 32t plus 6. We can look at the leading coefficient, see it's negative, which means that it opens down, which means it's going to have a maximum value at the vertex, hk. So we can find our vertex. Remember, h is equal to negative b over 2a, so negative 32 over 2 times negative 16, which is equal to 1. So that made it relatively simple. So 1 second is when we're going to hit the apex or the maximum height. Now, again, we could use k, our formula, to find it, or we could just plug this 1 in place of t. So substitute 1 for t to find the maximum value. So s of 1 is equal to negative 16 times 1 squared plus 32 times 1 plus 6, negative 16 plus 32 plus 6, or 22 feet. So the maximum height is going to occur at 1 second, and it's going to be 22 feet. So pretty straightforward. Projectile motion, anytime you deal with quadratics, like I said, you're going to see someone come up with a projectile motion problem. In fact, if you watch the movie October Sky, you will see that a projectile motion problem is what he used to prove that his rocket could not have started the fire of which he'd been accused. Let's do another example, fencing. A rancher has 200 feet of fencing to enclose 2 adjacent rectangular corrals. What dimensions will produce a maximum enclosed area? Now we are going to work on a couple assumptions here just because it makes it easier for us to work with. First of all, we're going to work on the assumption that the 2 adjacent rectangular corrals are both the same height or same length, depending on what way you're looking at it. And that they are we'll say that even that they are the same size and shape. So we're not going to be shifting things around. Both of those rectangles will be the same. So let's take a look at this and start into, okay, fencing. Now I'm going to find it much easier if I have a visual there. So I'm going to draw my 2 rectangular corrals. Right away, this helps me realize that we're sharing a fence line. So that middle fence line is going to count into both of those corrals, but is only going to count once towards my 200 feet. So I'm going to call the top of each of those corrals X. And I'm going to call the heights of the corral Y. So you'll see that we actually have, going into our 200 feet of fencing, we have 3 Ys and we have 4 X's, right? 2 X's on the top, 2 X's on the bottom. So I can say that 3y is equal to 200 minus 4x. If I start with the 200 and I take away all the lengths of the x's, then I'm left with the 3y's. So if I solve for y, that gives me y is equal to 200 thirds minus 4 thirds x. Now that I have x and y, I can find the area because the area of a rectangle is just length times width, right? So the length of the total, or I should say the area of the total space enclosed by those two rectangles is going to be 2x times the height of them, 200 thirds minus 4 thirds x. So I'm going to distribute through that 2x, and that's going to put me into a quadratic function. Ax is equal to negative 8 thirds x squared plus 400 thirds x. Looking at that, we see that the leading coefficient is negative. Therefore, it opens down, giving us a maximum at the vertex of hk. We can find hk by just using negative b over 2a. So we get, and in this case, what I did to save a little space and not deal with a lot of fractions when I'm drawing it out is I just said 400 divided by 3 is 133.3 repeating, and 8 divided by 3 is 2.6 repeating. So it's the same thing, just to simplify how it looked on the screen, I put it into a repeating decimal form. So h is negative 133.3 repeating over 2 times negative 2.6 repeating, which is equal to 25. So there's our x. So we can now find y by just plugging that x back up into that equation from above. Y equals to 200 thirds minus 4 thirds x. So if I do that, I get 200 thirds minus 4 thirds times 25, which gives us 33 and a third. So I have x, I have y. Looking at my total rectangle, set of rectangles here, I see that the two corrals side by side will be 2x, 25 times 2 or 50 feet, by 33 and a third feet. So those are the outer dimensions of these two corrals put together. You can see with that too, that now that we have that, we really could shift that middle fence, that middle Y, to either side and have the corrals, one of them wider and one of them narrower, and it really won't make a difference. It's still the same amount of fencing. Also, something you may have noticed here, or that may have thrown you off, is you go, well, wait a second, we're dealing with a set amount of fencing. Don't we get the greatest area by using a square? Because that's what you run into every time. You're like, oh, how do you find the maximum amount? And you go, oh, well, the largest rectangle you can get with a set perimeter is a square. But in this case, that doesn't quite work out that way because we're sharing that middle fence line. So that's what throws it off, where it doesn't work out as we expect. So the dimensions are 50 feet by 33 and a third feet. Let's look at another example, the revenue function. Revenue function, the amount of money you're going to make. This can be very important in business. The revenue function for a new plasma television is given by R of P is equal to 900P minus 0.1 P squared, where R stands for the revenue and P stands for the price. And this asks us what price P should be charged to maximize revenue. So what is the best price for us to charge to get the most revenue? Not the highest price we can charge, not the cheapest price we can charge, not where we can sell the most units, but what price is going to maximize our income, our revenue. And then what is the maximum revenue? Well, let's look at the equations. So we have R of P is equal to 900P minus 0.1 P squared. Well, first thing I'm going to do is I'm going to rewrite that in descending form. This is in ascending form. If I'm going to use the quadratic equation, if I'm going to use any of our formulas, I really want to rewrite it so that it's ax squared plus bx plus c. So I'm going to rewrite it as R of P is equal to negative 0.1 P squared plus 900P. I look at that leading coefficient, I see it's negative. That means it opens down, which means it's going to have a maximum at the vertex HK. I can find h by taking negative b over 2a. And again, that's where it's important that we have them in the right order so that we use the right terms. So negative 900 over 2 times negative 0.1 gives us 4,500. So that's our h. Well, then to find k, the output, we're just going to plug that 4,500 into our function. And I did this into my rewritten function. It would work the same if you plugged it into the original function. In fact, many times it may be better to plug it into the original function because then you know you don't have any mistakes on the way. So plugging that 4,500 in, we get 2,025,000. So the price for maximum revenue is to sell the TVs for $4,500 each. And that is going to give us a maximum revenue of $2,025,000. Now, I do apologize for this being a plasma screen at $4,500. I know that plasma screens have come down in price, and that's not necessarily what people are looking for these days. It might be an OLED or one of the other special curved screens and such that are being produced. So realize that this revenue function is a little outdated, but we could very much apply this to any sort of revenue that we want to come up with. So those were dealing with functions. We had functions, or we created functions from the vertex or from other information that we had. This one, where's my degree? We're going to start with data and come up with a quadratic model. So the following data represent the percentage of the population in a certain country aged 40 or older whose age is X, who do not have a college degree of some type. So do not have a college degree of some type. So we see that age is X, and then the output, I guess we'll say, is no college degree. And that's as a percentage. So 40-year-olds, 25.4% didn't have a college degree. 45-year-olds, 23.2%. 50-year-olds, 21.8%. 55-year-olds, 24.5%. 26-year-olds, 60-year-olds, 26.1%, and 65-year-olds, 29.8%. So we've got this data. Well, that kind of stinks, doesn't it? We have data. Well, how do we turn that into a quadratic model? Well, one thing we could do is we could plot these data points, kind of draw a parabola, determine where the vertex is, and then we could come up with the formula f of x is equal to a times x minus h squared plus k, and then take one of these data values, plug it into that formula so that we can find a and come up with it that way. We could do that, but that's messy and I'm going to say sketchy. Okay, so there's an easier way to do it, and we're going to use that easier way. So find a quadratic model that describes the relationship between age and percentage of the population that do not have a college degree. Then use the model to predict the percentage of 53-year-olds that do not have a college degree. Okay, so we've got this data and we want to do it. And how are we going to do it? Well, let's see. Where's my degree? The reality of it is we're going to use technology. Like I said, you could do the graphing, you could fight your way through there and get more or less, but we can use technology. Now, if you have a graphing calculator, then you can do that. You have the ability to do a quadratic regression, and that's what it will call it on your calculator, a quadratic regression. And you can plug in those data values and get the equation for the quadratic regression. I hate to admit it, but my calculator, as much as I love it, HP decided when they were doing graphing calculators that they would not give the ability for a quadratic regression. I can do all sorts of high degree regressions. I can do linear regressions. I can do all sorts of things on it, but they never built in a quadratic regression function. And I just haven't got around to writing a program for it that would allow my calculator to do a quadratic regression. So I can either switch over to one of the other calculators that I have, or since you've seen me use Desmos.com and such, I'm going to use another online tool, which is Quadratic Regression Calculator at kson.casio.com. And yes, unfortunately, that is the URL for that with that long number sequence afterwards. But it gives me the ability to plug in X and Y values, and then it will give me the coefficients for my quadratic equation. Now, it will do it in reverse instead of going descending order, which is what we like. It gives it in ascending order, but that's okay. It's easy enough for me to switch those around when I write it. So I did that. I plugged those data values, those right there, into that quadratic regression calculator, and I got the following quadratic equation. P of x is equal to 0.0296 x squared minus 2.9216x plus 94.6550. And of course, those coefficients are rounded, but that's what I got. So now that I have that, I have a quadratic function that relates the age of people over 40 and the percentage that do not have college degrees. That's the first part of the question. The second part of the question was to approximate the percentage of people who were 53 years old who did not have a college degree. So I'm just going to plug 53 into this equation. And because of the law of those numbers there, I'm not going to repeat the numbers. I'm just going to let you look at that. So once I plug that in, I find out a result of approximately 23%. So according to this quadratic regression, 53-year-olds without a college degree, approximately 23% of them do not have a college degree. And so we were able to see, dealing with some quadratic equations and finding the min and the max and some values, we also found that we can take some data if it's parabolic in nature, and we can come up with a quadratic function for that so that we can predict what might happen for certain values.